Just 290 million years after the Big Bang, a galaxy blazed into existence, spanning thousands of light-years, already rich with oxygen. Oxygen. An element cosmologists swore took at least 1 billion years to form. This discovery, made by the most expensive scientific instrument ever built, has left some of the world's greatest minds unable to sleep. On Christmas morning in 2021, while most of the world gathered around tables, tearing open wrapping paper, a rocket sat on a launch pad. It was carved out of the jungle on the northeastern coast of French Guiana. Inside its nose cone was something that had taken 30 years to build, cost $10 billion, and broken the hearts of nearly everyone who worked on it at least once. The rocket was an Ariane 5. Its payload, the James Webb Space Telescope. People who understood what was at stake were simply too terrified to cheer. In control rooms across Baltimore, Paris, and a dozen facilities throughout Europe, engineers sat with hands folded, eyes fixed on screens. They had spent years running through every possible failure scenario. Every motor that could jam. Every circuit that could go dark at the worst possible moment. They had counted 344 single points of failure during deployment alone. 344 moments where one stubborn latch, one misfiring actuator, would end the mission permanently. There would be no astronaut shuttle flying up to fix it. There would be no second chance. The telescope was heading nearly 1 million miles from Earth. Once it left, it was on its own. To understand why those engineers were holding their breath, you have to understand what the James Webb Space Telescope actually is, and why every single design choice was forced on its builders by the laws of physics themselves. Start with the mirror. 6.5 meters across, roughly the width of a large living room, it was made from 18 individual hexagonal segments. Each one was shaped from beryllium, a metal chosen because it is simultaneously lightweight and extraordinarily stable at extreme temperatures. Each segment was then coated in a microscopically thin layer of gold. Not for aesthetics, but because gold reflects infrared light better than almost any other material on Earth. Assembled together, those 18 segments form one of the most precise optical surfaces ever manufactured by human hands. The tolerances involved are almost impossible to describe in ordinary language. Imagine polishing a surface until its imperfections are smaller than a single atom. That is the scale of precision involved. But a mirror 6.5 meters wide cannot fit inside a rocket. Rockets have fixed dimensions, the mirror was simply too large. So, the engineers designed it to fold. The 18 segments were arranged into a central core and 2 hinged side panels that tuck inward, like wings folding against a bird's body. The entire structure collapses into a shape compact enough to fit inside the rocket fairing, then unfolds automatically in space. This sequence of mechanical maneuvers was so complex, and so dependent on every component functioning perfectly, that nothing like it had ever been attempted at this scale. The sun shield posed a different kind of challenge entirely. To detect the faint infrared glow of the earliest galaxies, the telescope's instruments needed to operate at -447 degrees Fahrenheit, a temperature close to absolute zero. Colder than the frozen vacuum between most stars. Any warmth, including the heat radiating from the telescope's own structure, would contaminate the signal and blind the instruments completely. The solution was a 5-layer thermal barrier, roughly the size of a tennis court, made from a material called capton. Each layer was aluminized to reflect heat away from the telescope side. On the sun-facing side, the shield absorbs enormous heat. On the telescope side, the temperature drops to nearly nothing. That gradient, across just a few feet of layered film, spans hundreds of degrees. It is, by any reasonable measure, the most sophisticated space blanket ever built. All of this engineering existed to serve a single purpose, to capture infrared light. Ancient light. When the universe was young, and the first galaxies were forming, they released energy at visible and ultraviolet wavelengths. But in the 13+ billion years since then, the universe has been expanding. Space itself has been stretching. As it stretched, it pulled those light waves along with it, elongating them from visible wavelengths into the infrared spectrum. By the time that ancient light reaches us today, it is completely invisible to human eyes. Every camera on Earth, every optical telescope ever built, cannot see it. Webb can, because Webb was built specifically to receive it. At 7:32 in the morning local time, the countdown reached 0 and the rocket climbed. The solar panels deployed 14 minutes after separation, and power flowed into the telescope for the first time in space. But being alive and being operational were two entirely different things. Ahead of the team lay the most complex deployment sequence ever attempted in the history of space exploration. The sun shield unfolded over 5 agonizing days. Each membrane tensioning across a frame the size of a tennis court, one increment at a time. Any tangle, any motor drawing the wrong current, could have crumpled it into useless wreckage. Then the secondary mirror swung out on 3 spindly support struts and locked into alignment. Then the 2 hinged side panels of the primary mirror rotated outward, each one clicking into permanent position. No mechanism existed to rehinge them if they stopped short. Controllers in Baltimore called out each latch as it engaged. A room that had been holding its collective breath for nearly 2 weeks allowed itself, for the first time, a few quiet tears. But the telescope was still not ready. Those 18 mirror segments, now fully extended, were each pointing in slightly different directions. Each one had to be individually adjusted using small actuators on its back, nudged by fractions of a millionth of an inch, until 18 separate reflections of a distant star slowly, painstakingly collapsed into a single sharp image. The alignment process took weeks. Engineers used a bright star called HD 84406 as their target, watching on screens as 18 ghost images converged one adjustment at a time. On March 11, 2022, the final alignment check came back clean. The mirror was one. Cold, perfect, and parked nearly 1,000,000 miles from home, pointed at the oldest light in existence. Then, on July 12, 2022, the White House hosted an event. The President of the United States stood before a screen and revealed to the world the first official science image from the James Webb Space Telescope. What people saw stopped them in their tracks. A field of thousands of galaxies covering a patch of sky so small that a grain of sand held at arm's length would have blocked the entire view. Every point of light in that image was not a star. Every point of light was an entire galaxy, containing hundreds of billions of stars. The celebration was genuine and widespread. But in research offices at universities across the world, some astronomers were already staring at those images with a growing sense of unease. Because what they were seeing did not look like what the models had told them they would find. And the telescope, as extraordinary as that first image was, had only just begun to look. Before the James Webb Space Telescope ever turned its golden mirror toward the sky, cosmologists believed they understood, in broad and confident terms, how the universe worked. That confidence was not arrogance, it was earned. Built piece by painstaking piece over decades of observation, calculation, and experimental confirmation. The model they had assembled was called lambda cold dark matter, and it was, by almost any measure, one of the most successful scientific frameworks ever constructed by human minds. The model began with a simple but staggering inventory. The universe, it said, is made of 3 components, none of which are evenly matched. Only 5% of everything that exists is ordinary matter, atoms, molecules, the stuff that makes up stars and planets and oceans, and you. 27% is something called cold dark matter. Invisible to light, detectable only through its gravitational effects on the galaxies it surrounds. The remaining 68% is even stranger, a property of space itself called dark energy, which drives the accelerating expansion of the universe. Together, these 3 ingredients, in those precise proportions, could reproduce almost everything astronomers had ever observed. The universe, it turned out, was mostly made of things that couldn't be seen, touched, or directly measured. But the math worked. And in science, when the math works this consistently, you trust it. The model also told a detailed story about how the universe's structure formed. In the earliest moments after the Big Bang, the cosmos was a near-uniform fog of hydrogen and helium, shot through with tiny fluctuations in density, scattered like ripples across an infinite ocean. Gravity pulled at those fluctuations. Dense regions attracted more matter. Over hundreds of millions of years, the fog collapsed into the first stars. Those stars gathered into the first small, primitive galaxies. And those dwarf galaxies slowly merged and accumulated into larger ones over billions of years. Small first, large later. Always. The process had a name, hierarchical structure formation, and it was one of the model's most fundamental and most tested predictions. Heavy elements were a key chapter in that same story. The early universe contained essentially no oxygen, no carbon, no iron, no silicon. Those elements did not exist until the first generation of massive stars forged them in nuclear furnaces burning at tens of millions of degrees, then scattered them across space in violent supernova explosions. After those explosions, a new generation of stars could form, incorporating the debris of the first. Then those stars died too, and a third generation formed, richer still, each cycle leaving the universe more chemically complex than it found it. Astronomers calculated that building up a meaningful quantity of oxygen, enough to detect spectroscopically inside a distant galaxy, required at least 1 billion years of this stellar birth, death, and recycling. That number wasn't a rough estimate. It was derived from detailed models of stellar physics, nuclear reaction rates, and supernova yields. It was considered one of the firmest timelines in all of cosmology. For decades, every observation pointed in the same direction. The Hubble Space Telescope peered into the deep universe and found exactly what lambda-cold dark matter predicted. The farther back you looked, the smaller and less developed the galaxies appeared. Infant structures, primitive clumps, raw material waiting to be assembled into something greater by the slow, patient hand of gravity and time. The universe had built itself gradually, the way a cathedral is built, stone by stone, generation by generation, according to a design that only becomes recognizable from a distance. It was ordered. It was elegant. It was consistent. And it matched the theory so precisely that many cosmologists began to wonder whether the great questions of cosmology might actually be answered within their own lifetimes. Not approximately answered, but fully answered. The kind of closure that comes when a centuries-long investigation finally delivers its verdict. The first sign that something was wrong did not arrive as a single dramatic discovery. It arrived the way most scientific crises do, quietly, in the margins, as a nagging feeling among researchers that the numbers weren't quite adding up. When Webb's earlier science images came back in the summer of 2022, the celebration was real and widespread. But among the astronomers who knew exactly what those images were supposed to show, a word kept surfacing in private conversations. Not in press releases, not in published papers, just in the hallways of universities and the back channels of academic email threads. The word was wrong. The earliest galaxies, according to every model, should look small and disorganized. The universe at that age simply hadn't had enough time to build anything bigger. What researchers were seeing in the Webb data didn't look like that. Some of those objects looked unexpectedly large, unexpectedly bright, unexpectedly structured. Richard Ellis, a cosmologist at University College London and one of the most respected observational astronomers alive, was among the first to say it publicly. Looking at the early data, he told colleagues he was worried. The objects appearing in those first images, he said, were monsters. It was not hyperbole. These galaxies, if confirmed, were too massive to have formed in the time available to them. The way a fully grown oak tree defies any explanation that it sprouted from an acorn planted last week. Then, in February 2023, a paper landed in the journal Nature that shifted the conversation from whispered concern to open confrontation. The authors, Devo Lab at Swinburne University of Technology in Australia, Erica Nelson at the University of Colorado Boulder, and a team of colleagues, had been analyzing Webb's early photometric data, measuring the light coming from extremely distant objects. What they found was difficult to process, even for the people who found it: 6 candidate galaxies, all of them existing between 500 and 700 million years after the Big Bang. And their masses, if the measurements held up, were extraordinary, up to 100 billion solar masses. 100 billion times the mass of our own star. Some of these objects, if confirmed, would rival the Milky Way in total size. The Milky Way took approximately 13 billion years to build. These candidates had apparently done something comparable in less than 1 billion. Joel Ledger, a galaxy evolution researcher at Penn State University, read the paper and offered a verdict that spread quickly through the astronomical community. These objects, he said, were in tension with 99% of cosmological models. Erica Nelson, one of the paper's lead authors, put it more directly. "It's just crazy," she said, "that these things seem to exist." The scientific community pushed back hard, and it was right to do so. Photometric measurements, estimates derived from the color and brightness of light across several wavelength bands, carry significant uncertainty. Dust inside a galaxy absorbs blue light and remits it as red, making a galaxy appear more distant than it actually is. Active galactic nuclei, the energetic cores of galaxies hosting massive black holes, can inflate apparent brightness dramatically. One by one, through 2023, researchers ran the candidates through the gauntlet of follow-up observation and independent analysis. Some of them didn't survive. A handful of the most dramatic early claims were revised downward when better data arrived. The skeptics felt vindicated. The models breathed again. Then came the spectroscopic confirmations, and that changed everything. Where photometric measurements estimate a galaxy's distance by analyzing the overall color of its light, spectroscopy breaks that light into its individual wavelengths and looks for specific chemical signatures. The absorption and emission lines of hydrogen, oxygen, carbon, magnesium. Each element has a known fingerprint in the spectrum. When you find that fingerprint shifted to a longer wavelength by a calculable amount, you have a precise measurement, not an estimate, of exactly how far away the galaxy is and exactly how fast the universe was expanding when its light left. The galaxies that survived spectroscopic scrutiny were fewer in number than the original candidates, but they were real. Verified not by one instrument or one team, but by multiple independent observations, all pointing to the same conclusion. These objects existed. They were as distant as the early measurements had suggested, and none of the counterarguments could explain them away. What the skeptical campaign had accomplished, ironically, was to sharpen the problem. By weeding out the candidates that could be explained, it had left behind the ones that couldn't. It was inside this charged atmosphere that the James Webb Advanced Deep Extragalactic Survey, known within the community as JADES, began returning its most consequential data. JADES was the most ambitious imaging and spectroscopic program the telescope would undertake in its early years. The goal was not to hunt for individual spectacular objects, but to do something more systematic and more powerful: build a complete, statistically meaningful census of the galaxy population in the early universe. Thousands of galaxies catalogued, redshifts confirmed spectroscopically. A map of cosmic history assembled layer by careful layer, the way a geologist reads rock strata. Most of what JADES found was consistent with prior knowledge, filling in gaps and refining measurements. But hidden inside its vast catalog, sitting at a redshift no one had previously confirmed, was a galaxy that didn't fit. The data around it accumulated slowly, checked and rechecked by multiple team members who each kept expecting to find an error. There was no error. And when the team finally announced its confirmed properties, it didn't strain the boundaries of what the standard model could explain. It broke them entirely. The galaxy's confirmed spectroscopic redshift was 14.32, meaning the light captured by Webb left this galaxy just 290 million years after the Big Bang. In a universe 13.8 billion years old, 290 million years is roughly 2% of all of cosmic time. The universe was, cosmically speaking, a newborn, and this galaxy was already there. But the redshift alone was not the deepest shock. The deeper shock was what the galaxy contained. It spans 1,600 light-years across. For comparison, the Milky Way stretches approximately 100,000 light-years from edge to edge. At 290 million years old, a galaxy of this kind shouldn't measure 1,600 light-years. It should be a smudge, a protogalactic fragment barely distinguishable from surrounding intergalactic gas. Its stellar mass, approximately 500 million solar masses, was already enough to challenge every model of how quickly gas can collapse and ignite into stars. Then the spectroscopy revealed oxygen. Oxygen does not form in the Big Bang. The Big Bang produced hydrogen, helium, and trace amounts of lithium, and nothing heavier. Every other element in the periodic table was forged later, inside stars. Oxygen specifically is produced in the cores of massive stars and scattered into space only when those stars end their lives in supernova explosions. For oxygen to be present in detectable quantities inside a galaxy, that galaxy must have already hosted at least one, and likely multiple, generations of stars that were born, lived out their full stellar lifetimes, and died violently. The Standard Model put that entire process at a minimum of 1 billion years. This galaxy was doing it at 290 million. Stefano Carniani, who led the analysis of the galaxy's spectral data, expressed the difficulty plainly. How, he asked, can nature make such a bright, massive, and large galaxy in less than 300 million years? It was not a rhetorical question. He and his colleagues genuinely did not have an answer. Sandor Shah, of Leiden University, working on the same data, reached for an analogy. It is like finding an adolescent, he said, where you would only expect babies. The light from this galaxy traveled 13.4 billion years to reach Webb's mirror. Due to the expansion of the universe during that journey, it now sits at a proper distance of approximately 33 billion light-years from Earth. We are not looking at something that exists in the universe as it is today. We're looking at a message from a time before our planet, before our star, before most of the stars in the Milky Way were born. And that message says something that no model predicted and no astronomer was prepared to hear. We were already here. We had already lived and died and scattered our remains across space. Whatever you thought came first, you haven't found it yet, If a single impossible galaxy could be dismissed as an anomaly, the universe was about to make that dismissal very difficult. Because just weeks after the confirmation of the galaxy at redshift 14.32, another discovery landed. And this one came with a subtitle that its authors chose without apparent irony. They called it, A Cosmic Miracle. Peter Van Dockum of Yale University and Rohan Naidu of the Massachusetts Institute of Technology announced a separate galaxy. This one at redshift 14.44. That number places it at just 280 million years after the Big Bang, 10 million years earlier than the previous record, pushing 10 million years deeper into the epoch that lambda cold dark matter understood least. By any measure of cosmic history, these two galaxies were neighbors in time. But where the first had stunned the community with its oxygen, this one stunned it with its structure. The galaxy spans approximately 500 light-years across. That is tiny by any modern standard, a fraction of the Milky Way's diameter. But at 280 million years old, it was not a featureless blob of young stars. It was organized. The spectral data revealed a galaxy undergoing a powerful burst of star formation, converting gas into stars at a rate that, scaled to its size, was extraordinary. And unlike many other unusual early galaxies that had appeared in Webb's data, this one showed no signs of an active galactic nucleus, no energetic black hole inflating its apparent brightness. The light was coming entirely from the stars themselves. Pure starburst. Nothing hidden, nothing inflated. To appreciate how deeply this violated the Standard Model, consider a comparison that Van Dockum and his colleagues offered in their paper. Sharks have been swimming in Earth's oceans for approximately 450 million years. They existed before trees. They outlasted the dinosaurs. They are, by any measure of biological history, ancient. This galaxy is younger than sharks. And yet it already shows the structural complexity and chemical maturity that lambda cold dark matter predicted would take billions of years to develop. The Standard Model's most fundamental prediction, small first, large later, always, was not being bent. It was being ignored entirely. The spectral data revealed something else as well, something that deepened the mystery rather than resolving it. The galaxy showed a high ratio of nitrogen to carbon, a chemical fingerprint that, in the present-day universe, is associated specifically with the densest, oldest stellar environments in the Milky Way, the globular clusters, ancient balls of stars that orbit our galaxy's halo and date back nearly to the beginning of cosmic time. Finding that signature in a galaxy just 280 million years old suggested it was not a primitive ancestor of later galactic structure. It was already chemically mature in ways the model simply couldn't account for. It had, in a sense, skipped adolescence entirely. Two galaxies, weeks apart, both at the edge of observable time, both impossible under the best theory humanity had constructed to explain the universe. And the James Webb Space Telescope had only just started looking. The crisis, however, was not limited to individual galaxies appearing too early. Something stranger was happening at a larger scale. Something that cut not just at the timeline of galaxy formation, but one of the most fundamental processes in all of cosmic history, reionization. The Great Transition. The moment the universe went from dark to light. In the first moments after the Big Bang, the universe was a plasma of charged particles, opaque to light. Then it cooled. Neutral hydrogen formed. And for hundreds of millions of years, the cosmos went genuinely dark. No stars, no galaxies, just hydrogen and helium drifting in gravitational wells, waiting. This period is sometimes called the cosmic dark ages. Then the first stars ignited, the first galaxies formed, and the ultraviolet radiation pouring from those early sources began ionizing the surrounding hydrogen gas. Burning through the fog the way sunlight burns through morning mist. As ionized bubbles grew and merged, the universe became transparent. That transition is reionization. The established timeline held that it began around 400 to 500 million years after the Big Bang, and was essentially complete by 1 billion years. This was not a rough estimate. It had been derived from observations of distant quasars, confirmed by the Planck satellite, and incorporated into the Standard Model as one of its firmest chronological anchors. It was, in the language of the field, settled. Then Webb detected something that settled science cannot accommodate. A galaxy, sitting at 330 million years after the Big Bang, was shining in a specific ultraviolet wavelength called Lyman alpha radiation. This matters enormously, because Lyman alpha photons have one defining characteristic in the early universe: they should be completely invisible to us. The early cosmos was filled with neutral hydrogen gas, a thick fog stretching across billions of light-years. And that fog is extraordinarily efficient at one particular job: absorbing Lyman alpha radiation. Photons at that wavelength enter the fog and simply vanish. The Standard Model was explicit on this point. Any Lyman alpha signal from before reionization was erased in transit. Period. Kevin Hainline of the University of Arizona, one of the researchers analyzing the data, put it plainly: we really shouldn't have found a galaxy like this. For the signal to have reached Webb's mirror, something extraordinary had to have happened. Either the galaxy itself had created a bubble of already ionized gas around it, a cleared region large enough to let the photons escape, or the fog was never as thick as the models assumed. Patchier, and more transparent in certain regions than the standard timeline allows. Either interpretation leads to the same conclusion: reionization began significantly earlier than cosmologists had calculated. A 2024 paper published in the monthly notices of the Royal Astronomical Society put a number on the discrepancy. Reionization, the paper concluded, ended approximately 350 million years earlier than models predicted. Then it went further. The authors stated directly that the lambda cold dark matter timeline simply cannot accommodate the combined Webb and Planck observations, even if exotic fixes are introduced. That last clause is the one that matters. Not that the model needed an adjustment, but that the model's timeline was incompatible with observation at a level that adjustments could not bridge. 350 million years is not a small correction buried in a large number. Those 350 million years sit at the very beginning of cosmic history. In the most sensitive and consequential interval in the universe's entire life, when conditions were most extreme and the foundational processes that shaped everything that followed were running at full speed. Getting that window wrong is not a rounding error. It is a structural failure. Charlotte Mason of the University of Copenhagen, one of the leading researchers on reionization, described the reaction inside the field with characteristic understatement. Everyone, she said, was freaking out. And they were freaking out for good reason. Because the anomalies were no longer arriving one at a time, from one instrument, from one research group, pointing at one corner of the standard model. They were arriving together, from different telescopes, different methodologies, different teams on different continents. And they were all pointing in the same direction. But even that was not the deepest problem. Because while astronomers were grappling with galaxies that appeared too early in light that should have been swallowed by the fog, a completely separate crisis was unfolding in a different part of the data entirely. One that didn't involve the distant universe at all. One that involved a single number. A number that the entire architecture of modern cosmology depended on getting right. And that number, measured two different ways by two different methods using two different instruments, was producing two different answers. The gap between them had a name. Cosmologists called it the Hubble tension. And in 2024, after James Webb weighed in directly, it stopped being a tension. It became a crisis. Every so often, science produces a number that becomes load-bearing. A single value that so much else depends on, that if it shifts, the entire structure above it has to be reassessed. The Hubble constant is that kind of number. Named after Edwin Hubble, who first measured the expansion of the universe in the 1920s, it describes the rate at which the cosmos is currently growing. Measure a galaxy's distance. Measure how fast it is receding from us. Divide one by the other. The result tells you how quickly space itself is stretching. And from that single value, you can calculate the age of the universe, the rate at which structure formed, and the ultimate fate of everything that exists. Get it right, and the whole model coheres. Get it wrong, and every calculation built on top of it is quietly, invisibly corrupted. For decades, cosmologists argued about the precise value of the Hubble constant. By the early 2020s, two methods of measuring it had emerged as the most credible, and they disagreed. Not slightly. Not within the margin of error that scientists routinely absorb and move past. They disagreed at a level that, in the language of physics, demands an explanation. The first method worked by looking backward in time. The Planck satellite had mapped the cosmic microwave background, the faint afterglow of the Big Bang, with extraordinary precision. From those measurements, physicists could calculate the early universe's expansion rate and extrapolate it forward to the present day. The Planck result, 67.4 kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light-years. For every additional megaparsec of distance between us and a galaxy, that galaxy is receding 67.4 kilometers per second faster. That is the universe's expansion rate, derived from its very first light. The second method worked by measuring nearby objects directly. Adam Rees of Johns Hopkins University, a Nobel laureate, led a collaboration that used two types of cosmic distance markers, Cepheid variable stars, which pulse at rates directly tied to their luminosity, allowing astronomers to calculate their true brightness and therefore their distance. And Type 1a supernovae, stellar explosions so consistent in their peak brightness that they function as what astronomers call standard candles. Objects whose true luminosity is known, making their distance calculable from how bright they appear. Using these markers across hundreds of galaxies, Rees and his colleagues measured the current expansion rate from local, direct observation. Their result, 73 kilometers per second per megaparsec. 67.4 and 73 sound small. It is not small. The statistical significance of that discrepancy had reached 5 sigma, the formal threshold in particle physics for declaring a discovery. Flipped around, a 5 sigma disagreement between two measurements of the same quantity is the formal threshold for saying that something is seriously, possibly fundamentally wrong. Not probably wrong. Not suspiciously wrong. Wrong at the level where the scientific community is obligated to take the problem seriously. Some physicists argued the discrepancy might be a systematic error in the local measurement. The Cepheid observations, they noted, were made using the Hubble Space Telescope, an instrument with a resolution limit that, in crowded stellar fields, might be blending the light of multiple stars together and misidentifying them as single Cepheids. If the distance markers were contaminated this way, the local measurement would be artificially inflated. It was a credible hypothesis, and it was exactly the kind of hypothesis that the James Webb Space Telescope, with its vastly superior resolution, could test directly. In December 2024, RISA's team published their James Webb analysis of the same Cepheid fields. With Webb's sharper eye, they could separate stars that Hubble had blurred together. The measurement error, it turned out, was not the problem. The Webb result for the local expansion rate came in at 72.6 km per second per megaparsec. Within measurement uncertainty of the original Hubble value, and still firmly separated from the Planck number by the same stubborn gap. Daniel Skolnick of Duke University responded to the findings directly. The Hubble tension, he said, is now a Hubble crisis. Rees himself was precise about what the James Webb result meant. With measurement errors negated, what remains, he said, is the real and exciting possibility that we have misunderstood the universe. 2 independent methods, 2 verified measurements, 1 universe, 2 different answers. And the instrument built to resolve the disagreement had instead confirmed it. The question that followed was the one that keeps theoretical physicists awake at night. If the early universe and the late universe give you different expansion rates when measured by independent, verified methods, what does that actually mean physically? It cannot mean that the universe is expanding at 2 different rates simultaneously. It must mean that something in the history of cosmic expansion, something between the Big Bang and today, is not accounted for in the standard model. Something happened. Something that the model doesn't contain. 3 explanations are currently in serious circulation. And each one, if confirmed, would require rewriting chapters of cosmology considered settled for decades. The first is early dark energy. Mark Kamiankowski of Johns Hopkins University proposed that in the first few 100,000 years after the Big Bang, some additional form of energy existed briefly. A short burst of repulsive force that slightly accelerated expansion beyond what the standard model predicts, then faded away completely, leaving no direct trace. If that surge existed, it would shift the Planck-derived Hubble constant upward, closing the gap with the local measurement. The mathematics is coherent. The problem is that early dark energy has never been detected. There is no confirmed observational fingerprint. It is a term added to an equation specifically because the equation produces the wrong answer without it. The second possibility is that dark energy, the force driving the current acceleration of the universe, is not the fixed, constant property of space that the standard model assumes. Perhaps it changes over time. Some early 2025 data from the Dark Energy Spectroscopic Instrument Survey suggested dark energy might be weakening. If confirmed, that would reshape the late universe's expansion history, and potentially close the gap from the other direction. But as of early 2026, that result remains unconfirmed. The third possibility is the most radical of all. Perhaps the cosmological principle itself is incomplete. The cosmological principle states that the universe, at large enough scales, is the same in every direction, uniform, isotropic, with no preferred axis and no special location. It is the mathematical foundation beneath the entire standard model. The equations that describe cosmic evolution assume it. Pull that assumption out, and the formal structure of modern cosmology needs to be rebuilt from different starting conditions. If the universe is not perfectly uniform, if it has directions it prefers, asymmetries inherited from the Big Bang itself, then using an early universe measurement to predict a late universe measurement becomes formally invalid. The 2 answers diverge not because something is wrong with the physics, but because the universe is not the kind of place the model assumed it was. Each solution requires the existence of something that has not been directly observed. Early dark energy is undetected. Evolving dark energy is unconfirmed. A violation of the cosmological principle at the required scale remains unproven. Cosmology is being asked to choose between 3 types of unknown physics without enough data to rule out any of them definitively. And here is the deeper discomfort lurking beneath all 3 options. Lambda cold dark matter already requires two invisible, undetected ingredients. Dark matter, which accounts for 27% of the universe's total mass and energy, and has never been directly observed in any laboratory on Earth. And dark energy, which accounts for 68% of everything, and whose physical nature remains completely unknown. Ordinary matter, everything you can see, touch, or measure, makes up just 5% of what the model describes. Add early dark energy, and the model now requires three separate undetected components. Three invisible pillars holding up the entire architecture. Alison Kirkpatrick, a professor of astronomy at the University of Kansas, who had spent her career building research programs on the predictions of lambda dark matter, gave an interview in 2023 that landed differently for scientists than it did for the public. Right now, she said, I find myself lying awake at 3 in the morning, wondering if everything I've ever done is wrong. That sentence is not a confession of defeat. It is something more precise than that. It is what it sounds like when a scientist, trained to trust a framework, begins for the first time to genuinely doubt it. Not because the data is ambiguous, but because the data keeps arriving from every direction, telling the same uncomfortable story. The map is wrong. And nobody yet knows how wrong, or where to draw the new one. Science does not collapse dramatically. It does not wake up one morning, look at the data, and declare itself defeated. What it does, what it has always done across every major revision in the history of human knowledge, is argue, resist, patch, and eventually, when the weight of evidence becomes impossible to redistribute, rebuild. We are somewhere in the middle of that process right now. Understanding where exactly requires stepping back from the individual anomalies and looking at the shape of the crisis as a whole. The defenders of lambda cold dark matter are not in denial. Their argument is not complacency. It is historical track record. The model has been challenged before, and has absorbed the challenge each time through improvements in simulation fidelity and a better understanding of how stars form, explode, and feed back energy into the gas around them. The early galaxy anomalies, in this view, reflect the extraordinary complexity of gas dynamics in the infant universe, not a failure of the underlying cosmological framework. These researchers are not dismissing Webb's findings. They are betting that sufficient computational refinement will eventually bring the simulations back into agreement with the observations. It has happened before. It could happen again. A second group believes the model requires fundamental revision rather than incremental adjustment. They point to the number, variety, and consistency of the anomalies as evidence that the model's core assumptions, not merely its secondary parameters, are under genuine strain. Too many galaxies appearing too early. Reionization ending 350 million years ahead of schedule. A Hubble constant that measures differently depending on which end of cosmic history you look from. A galaxy producing oxygen at 290 million years when the physics of stellar evolution says it needs at least a billion. These researchers are not predicting imminent revolution. They're arguing that the field needs to seriously investigate modifications to the dark matter prescription, alternatives to cold dark matter, and potentially revised treatments of how dark energy behaves across cosmic time. A third group, smaller but growing, uses a word that mainstream cosmology has historically avoided: paradigm shift. These researchers argue that the accumulation of Webb anomalies, taken together with the Hubble tension and the large-scale structure discrepancies, points toward a fundamental incompleteness in the current model, one that cannot be patched, only replaced. What is striking is not that this group exists. Heterodox thinkers exist in every field. What is striking is that their papers are now appearing in the leading astrophysical journals, being taken seriously at major conferences, and attracting collaborators who 5 years ago would not have entertained the conversation. One of the ideas gaining the most unexpected traction is one that spent 4 decades in the scientific wilderness. In 1983, an Israeli physicist named Mordechai Milgram published a paper proposing something radical. Instead of explaining why galaxies rotate faster than their visible matter should allow by adding invisible dark matter, he proposed modifying the law of gravity itself. Specifically, he suggested that at very low accelerations, far below anything measurable in the solar system, gravity behaves differently than Newton's equations predict. It falls off more slowly with distance. The result, the outer regions of galaxies feel more gravitational pull than standard physics would generate, without any dark matter required. He called the framework modified Newtonian dynamics, or MOND. For the next 4 decades, mainstream cosmology largely ignored it. Lambda cold dark matter was extraordinarily successful at larger scales, and MOND struggled to account for the behavior of galaxy clusters without invoking some form of additional mass. It was relegated to the scientific margins, kept alive by a small community of researchers operating at the edges of the field, waiting for data that would force the center to listen. James Webb has not vindicated modified Newtonian dynamics. But it has forced cosmology to stop pretending the alternative doesn't exist. Researchers who were once told they were wasting their time are now being invited to collaborate. Their predictions are being tested against Webb data with genuine openness. The dismissal is over. Meanwhile, a different and stranger idea has been gathering support from within the mainstream itself. What if the universe didn't wait for stars to die before it built its first black holes? The standard picture of black hole formation runs through stellar death. A massive star exhausts its fuel. Gravity wins. The core collapses. It is a process measured in millions of years of stellar evolution. Lambda cold dark matter predicts that the earliest black holes formed this way, and then grew gradually by consuming surrounding matter over billions of years. But Webb keeps finding supermassive black holes in the earliest epochs of the universe that are too large for this story. Black holes containing hundreds of millions or even billions of solar masses, already fully grown in a universe only a few 100 million years old. The standard formation pathway cannot produce objects that massive that quickly. The numbers simply don't work. The primordial black hole hypothesis offers a radically different origin story. In the first fractions of a second after the Big Bang, space was violently uneven, shot through with regions of extreme density fluctuating against regions of relative emptiness. Wherever those density fluctuations exceeded a critical threshold, gravity could have overwhelmed the outward pressure of the newborn universe and collapsed those regions directly into black holes. No stars required. No millions of years of waiting. These primordial black holes would have existed from nearly the very beginning, serving as gravitational scaffolding around which gas could pile up, compress, and ignite into stars at rates that standard models cannot generate. The result would be galaxies that assembled far faster than the hierarchical model allows. Exactly the kind of galaxies Webb keeps finding. What all of these competing ideas share is an acknowledgement that the standard model, as currently constructed, is leaving something out. The question is what? And the honest answer, as of early 2026, is that nobody knows. The field is not unified. It is not quietly confident. Inside the community, there is a real and widening distribution of opinion about what Webb's findings actually mean. And a large fraction of working cosmologists, when asked privately, will admit that they are genuinely uncertain. They're continuing to publish, continuing to refine, continuing to work within lambda dark matter because that is the framework that has the tools, the predictions, and the community. But the certainty that characterized the field after the precision measurements of the early 2000s has quietly eroded. One senior cosmologist, speaking at a workshop in 2024, put it plainly, "The data," he said, "is telling us something. We don't agree on what. The next instrument in line to weigh in is already being assembled." The Nancy Grace Roman Space Telescope, named for the astronomer who was instrumental in creating the Hubble program, is designed with a field of view 100 times larger than Webb's. Where Webb sees a postage stamp of sky, Roman will see a poster, at sensitivity levels that bring faint, distant galaxies into statistical clarity across hundreds of millions of objects. Its anticipated launch in the late 2020s is not a routine next step in a smooth scientific progression. In the context of everything Webb has found, it is a verdict machine. Roman will measure the Hubble constant through multiple, entirely independent methods. It will survey the distribution of galaxy masses across billions of years of cosmic history. And if massive early galaxies are genuinely overabundant compared to lambda cold dark matter's predictions, the statistics across millions of objects will make that undeniable. It will probe the behavior of dark energy across cosmic time with a precision no previous instrument has achieved. If the anomalies are real, Roman will confirm them at a scale that leaves no room for alternative interpretation. If they are statistical flukes produced by Webb sampling a particularly unusual region of the universe, Roman will reveal that too. Either answer resolves questions currently worth decades of theoretical labor. Either answer moves the field forward. But here is what no instrument can resolve: the human dimension of what is happening right now. The astronomers working with Webb's data are not a monolith of crisis. Many of them describe the experience with something closer to exhilaration. The genuine, electric feeling of being the first human beings to see something no one has ever seen. That feeling coexists, sometimes in the same person, sometimes in the same conversation, with a quieter anxiety about what the data means for everything they were trained to believe. Alison Kirkpatrick, who said she lay awake at 3 in the morning wondering if everything she had ever done was wrong, has not stopped working. She's still analyzing the data, still publishing, still contributing to a community that is, in its best moments, collectively honest about the limits of its own knowledge. That honesty is not a weakness of the scientific process. It is the process functioning correctly, producing data that challenges assumptions, forcing revision, creating the productive disorientation that precedes genuine understanding. The telescope that produced all of this is still up there, orbiting a gravitational equilibrium point nearly 1 million miles from Earth, cooling itself to temperatures colder than deep space, pointing its gold mirror at the oldest light in the observable universe. It is sending home data that no one fully understands yet. A galaxy that produced oxygen before the models say oxygen was possible. A universe that expands at one rate when you measure it from the beginning, and a different rate when you measure it from where we stand. A cosmos that built massive, structured, chemically mature galaxies in a fraction of the time anyone thought the laws of physics allowed. These are not small discrepancies at the edge of a well-understood picture. There are cracks running through the foundation. And the most powerful observatory humanity has ever pointed at the sky has only been operational for 3 years. Whatever the universe is, it is more surprising than the model predicted. More structured, more ancient in its complexity, more resistant to the neat timelines we drew for it. That is not a failure. That is the finest possible outcome of a scientific instrument, to show us that reality is richer and stranger than our best current theories. Every generation of astronomers has inherited a map from the one before. Every generation has discovered that the map, however carefully drawn, does not fully match the territory. The generation working with Webb's data right now may be the one that finds out just how different the map and the territory really are. The scale of this realization is not just academic. It challenges our fundamental understanding of creation itself. We thought we knew the blueprint, the step-by-step assembly instructions for everything. Now, faced with these impossible objects, these cosmic anachronisms, we are forced to admit that the universe began its grand work with a speed and an intricate artistry we utterly failed to foresee. It suggests a universe not gradually awakening, but bursting forth with an almost instantaneous complexity, forging elements and structures long before our carefully calculated cosmic clocks allowed. It means that the very fabric of existence, from its earliest moments, defied our expectations. This isn't a minor tweak to a formula, it's a whisper from the deep past, suggesting that the initial conditions, the fundamental constants, or even the laws of gravity as we comprehend them, are incomplete. It's an invitation to confront a reality that is far grander, and far more unsettling, than our human-made frameworks can yet contain. The silence from the academic hallways, the shared anxiety among brilliant minds, is the sound of an edifice creaking. It is the sound of certainty giving way to a profound, exhilarating uncertainty. The universe, it seems, has a secret it's finally ready to share, and it's one that will reshape our understanding for generations to come. As the gold mirror patiently gathers more light, each photon carries a fragment of that secret, a piece of a story we are only beginning to know how to read. A story of objects appearing when they should not, built of materials that should not exist. A story of a universe that achieved the impossible in less than 300 million years. The journey of light from these impossible galaxies has spanned over 13 billion years, now reaching an Earth that is itself only 4.5 billion years old. These ancient messages, traveling across 33 billion light-years of expanding space, whisper of giants that formed when the cosmos was barely 2% of its current age. They speak of galaxies, some as massive as 100 billion times our Sun, already ablaze with oxygen, when the models decreed only primordial gas should exist. We thought we were close to knowing everything, but the universe keeps showing us the raw, shocking truth: our understanding is still profoundly, terrifyingly, incomplete.